Alright, so we're doing number 59, which is the only red problem in chapter 11. So part A asks you, you have a disk that's being rotated around its center with a radius r and a mass of m, and then it's being set into motion until it reaches pure rolling motion. So part A asks you to find the time it takes to get to pure rolling motion, and this is so our answer is gonna be in like these variables. Okay, so we have to know that momentum equals the force times time. Well, actually, like the change in time and then the change in momentum. So the change in momentum equals force times time, and then the only force here is the frictional force. So this would be friction. All right, and then delta P equals m delta V, and then friction is friction, and then times the self time. Okay. Now, delta V is going to equal r omega. That's just like, so velocity equals the radius times angular velocity. So m r omega equals friction times the change in time. And then we'll solve for the change in time. So we get m r omega over friction, which is also mu times the normal force. And then the normal force is equal to mg. So I'll change the normal force to mg. And then our m's cancel out, so then we get r omega over mu g, which I think is our answer. Okay, so on part B, asks you to find the distance the disk travels before it reaches pure rolling motion, and then this is like a two-step problem. So first we have to find the angular the angular velocity it's at pure rolling motion, and then we use that to find the distance by plugging it into work. So the angular momentum before it reaches pure in the beginning is the same. It's conserved, so it's the same as when it reaches pure rolling motion. So then we know that the moment of inertia of a disk is 1/2 mr squared. And then, so we're going to solve for omega. And then, so if I'm going to skip all the steps of algebra, but basically after you do all the algebra, you'll get omega equals 1/3 of omega initial. And then, so now we're going to use work. Work is the change in kinetic energy, and that would be 1/2 mv squared. And then V, we said V equals r omega, right? So we'll plug in r omega for V. And then, now we found what omega was in the first part of our part B. So that equals 1/2 m r 1/3 omega initial squared. And this equals 1/18 m r squared omega initial squared. Now, work also equals the F delta x, and the only F here is friction, so it equals friction delta x. And then, so if we plug in everything for here, we're gonna solve for delta x. So what we got for work was this 1/18 m r squared omega initial squared equals friction delta x, and then delta x equals then 1/18 m r squared omega squared over friction, which is also mu mg, and then Oh, yeah, that's my answer. Because that's the answer that the book has to find for you.